नमस्कार बच्चों, मेरा नाम धन्या और हम लोग ग्रेड 11 केमिस्ट्री का 4th लेसन सीख रहे हैं जिसका नाम है केमिकल बॉन्डिंग. And today, in today's video, we are going to learn about van der Waals forces. You can see the objectives. Also, we will be learning the different types of van der Waals forces and also the factors on which this depends upon. Okay, so starting with van der Waals forces. Okay, so what is this van der Waals force? Okay, let's start with what is van der Waals forces. Okay, now students, van der Waals forces are forces of attraction that can exist between molecules or atom. So they are forces of attraction, attractive forces that keep the atoms or molecules together. Forces of attraction between atoms or molecules. So these are responsible for keeping the atoms and molecules together. Now, if you ask whether they are strong or weak, they are not very strong. They are weak forces of attraction that keeps the atoms or molecules together. Okay, so it can exist between, so we can say these are intermolecular forces of attraction that is present in gases, liquids, and solids. Okay, so they are called as van der Waals forces. Okay, now these are weak forces compared to covalent bond, ionic bond, etc. Now, because this name is very long, I will be using van der Waals force shortcut. Okay, just for saving the time. Okay, so van der Waals forces are the weak forces of attraction that exist between atoms and molecules. Right. Now, interactions. Forces of attraction or interactive forces. Interactive forces between atoms or molecules, they are of two types. Okay. One is strong interactive forces. Strong interaction may exist, or it can be weak interactive forces. So attractive forces or interactive forces can be of two types, strong interaction or weak interaction forces. Strong interaction, you have already studied the strong attractive forces, which are ionic and covalent bonds. So what kind of attraction exists in ionic and covalent bonds? Strong interactive forces. Okay, now for weak interactive forces is for molecules that have weak forces of attraction between them, and that is nothing but one is van der Waals force and one is hydrogen bond. Okay, so you have already learned about ionic and covalent bond. And in today's video, we are going to learn about the weak interactive forces of attraction that exist between atoms or molecules that keeps them near to each other. Okay, so this is called as van der Waals forces. Okay, so about hydrogen bond, we will be learning in the next video. This van der Waals force was discovered by J.D. van der Waals, and he was a scientist who discovered van der Waals forces, and that's why the forces are in his name. Okay, so these are weak forces of attraction or intermolecular forces of attraction between atoms or molecules. Now, van der Waals forces, so I'm just writing as short form, can exist between, they can exist between two non-polar molecules. You know what is non-polar molecules now. Polar means those who have a dipole moment. My last video was about dipole moment. So those who have a dipole moment, they are polar. Those whose dipole moment is zero, they are non-polar. Okay. Now they can exist. So non-polar molecule like hydrogen, oxygen, chlorine. Okay. There are more examples. You can see the video. Okay. It can also exist between two polar. Polar means those who have a dipole moment. Yes, water is an example of a polar molecule. Then also between one polar and one non-polar. Okay. They can also exist between an ion and a polar molecule. Ion and non-polar molecule. They can also exist between any two molecules. So van der Waals forces, they can exist between two non-polar molecules, two polar. It can be one polar, one non-polar molecule. It can be between ion and polar or ion or non-polar, between any two molecules also. Okay. Now from here, we will look at the different types of van der Waals forces, the types. Okay. So the different types of van der Waals forces. The first one, or the first type, is ion dipole interaction. Ion dipole interaction. What is an ion dipole interaction? You know what's the meaning of ion? Yes, it can be a cation. It can be an anion. Yes, it can be a cation or an anion. So ion can be a cation or anion, and dipole means polar molecule. So basically, it is the interaction between cation and a polar molecule or an anion and a polar molecule. For example, if I take Cl minus, this is an anion, right? Now, I take a polar molecule like HCl. Now, HCl is polar. That means chlorine will develop a slight negative charge and hydrogen will develop a slight positive charge. Now, there's a negative charge for this chloride ion. So that is why there will be forces of attraction between chloride ion and hydrogen ion. Yes, between chloride ion and the hydrogen of chloride. So this force of attraction between the chloride ion and this polar molecule is called as ion dipole interaction. Okay, so in the presence of chloride ion, what is happening? There is attraction between weak forces of attraction, though. There is attraction still. There's weak force of attraction between chloride ion and the hydrogen. And this force of attraction is called as ion dipole interaction. Okay, and among all the different types of van der Waals force, this is the strongest. Okay, so this is ion dipole interaction. So this is between a cation, anion. So this is between an anion and polar molecule. Okay. Then it can also exist between a cation and a polar molecule. For example, if I take sodium chloride, when you dissolve in water, I get sodium ion and chloride ion, right? Now, I have the sodium ion, which is surrounded by water molecules. Okay, so this is water molecules. All these are water molecules. All these are water molecule. Now, because this is water is a polar molecule. Water is a polar molecule. So we drew the structure when we were doing dipole moment, oxygen, hydrogen, and hydrogen. Okay. So oxygen develops what? A slight negative charge. Yes. So I have the negative charge over here and positive charge of water over here. Negative charge here, positive charge here. Negative charge here, positive charge here. They align in such a way that the water dipole that surround the sodium chloride, the negative charge of oxygen is attracted to the positive sodium. So if I draw like this, I draw all the water molecule is aligned in such a way that the negative charge of oxygen is attracted to the positive charge of sodium. Okay, see, there's a weak force of attraction between the negative charge of oxygen and the positive charge of sodium. And that is why sodium chloride is soluble in water. And this weak force of attraction between the cation and a polar molecule is also called as ion-dipole interaction. Okay, so the negative charge of oxygen attracts the positive charge of sodium. Okay, so this is ion-dipole interaction. So go with the name. Cation and a polar molecule. Anion and a polar molecule. That's it. Okay, so this is an example. And this is strongest among all the there are 5 types of van der Waals forces. So this is the strongest, right? Now, coming to the next type, which is called as, so this is the strongest. So this is number 1. So I have the next type, which is called as dipole-dipole interaction. Dipole-dipole interaction. Dipole means polar. Dipole means polar. Okay. So I have a polar molecule, example, hydrogen chloride. Okay. Again, another polar molecule, hydrogen chloride. Okay. Now, this is already polar. So chloride will develop a negative charge. Hydrogen will develop a positive charge. Here also, hydrogen will develop a positive charge. Chloride will develop a negative charge. So what would happen between the negative chloride ion and the positive hydrogen ion? There can be weak forces of attraction between them, and this is called as dipole-dipole interaction. That means interaction between 2 polar molecules. Okay, and this has second highest strength. The first strongest is ion-dipole interaction. The second strongest is dipole-dipole interaction. Okay, I hope it is clear. Dipole-dipole interaction means the interaction between 2 polar molecules. That's it. Okay. Coming to the third type of interaction, which is called as ion-induced dipole interaction. What is this ion-induced dipole interaction? Induced dipole interaction. Okay. So that means it exists between an ion and a non-polar molecule. For example, if I take, suppose, maybe hydrogen molecule, which is non-polar, and I take an ion, maybe bromide ion. Okay, so I'm taking an ion and I'm taking a non-polar molecule. Now you can see here, there is a negative charge, right? Now, because of this negative charge, or under the influence of this negative charge, this hydrogen gets polarized, okay? And this might develop a positive charge, and this hydrogen may develop a negative charge. And as a result, so now how is the hydrogen now? Has it become temporarily polar? It has become temporarily polar under the influence of an ion. So this ion has induced polarity. That means because of this ion, this non-polar molecule is becoming polar just for some time. And what is happening? There is interaction between this bromide ion and the hydrogen. So this is not very strong, okay? And this is called as ion-induced dipole interaction. So students, ion-induced dipole interaction exists between an ion and a non-polar molecule. That is, bromide ion is the ion and hydrogen, suppose any non-polar, nitrogen, oxygen, any non-polar molecule. Now, under the influence of the ion, this non-polar molecule becomes temporarily polar. That means this ion is inducing the polarity, making it polar for some time. And when it becomes polar, there is interaction between the ion and the non-polar molecule. And this is called as ion-induced dipole interaction, which is not very strong. This is very weak compared to the other two that we studied. So compared to ion dipole and dipole dipole, ion-induced is very weak. Okay. I hope till here it is clear. Okay, when we practice more questions, it will be more clear. Now, the next type, the fourth type is, so just go with the name, that's it. Fourth one is dipole-induced dipole interaction. So that means this exists between a polar, dipole means always polar, okay? A polar molecule and non-polar molecule. For example, if I take a polar molecule, for example, hydrogen chloride, okay? So I take hydrogen chloride and a non-polar molecule may be chlorine or oxygen or nitrogen or hydrogen, any non-polar molecule, okay? And hydrogen chloride is polar, so chloride, there is a negative charge. Hydrogen, there's a slight positive charge. Now, under the influence of this polar molecule, this non-polar is getting polar. okay, just temporarily, and this develops a slight positive charge and this develops a slight negative charge. In other words, because of the negative charge that has come here, in chlorine molecule, the negative charge the electron seems to move on to this chlorine, which is further away. And as a result, this chlorine develops a slight positive charge. Or rather, this polar molecule makes the chlorine slightly polar. So that means, isn't it inducing polarity just like we saw the previous one? Slightly polar. So inducing polarity. That means making non-polar molecule slightly polar. Okay. And now what would happen? There will be forces of attraction between the two chlorine. And this weak forces of attraction is called as dipole-induced dipole interaction. So under the influence of the polar molecule, the non-polar molecule is becoming polar, and then there will be forces of attraction between the polar and the non-polar molecule. Okay. So this is called as dipole-induced dipole interaction. So non-polar can be chlorine molecule, hydrogen, oxygen, nitrogen. All these are non-polar. Okay, I hope it is clear till now. The last one, the last type of dipole-dipole interaction is instantaneous dipole-induced dipole interaction. Instantaneous, at any instant of time. And this exists between non-polar and non-polar molecule. Two non-polar. How is this possible? Two non-polar molecule. What happens? Okay. So instantaneous means at any instant of time. Okay. So I take a non-polar molecule, hydrogen, any oxygen, nitrogen, any non-polar molecule. I take another non-polar molecule. Okay. Now, we know that any molecule, the electron is behaving as a wave, that we know. And the electron at any instant of time, sometimes there is more electron density at one side, at one area. So the other area that is deficient of electron will have a slight positive charge, and repeatedly I'm telling, not permanent at any instant of time. Okay, so at this particular time, this hydrogen has become a dipole, okay, temporarily, just for some time, maybe split of a second or sometimes, okay. So at a particular instant of time, this hydrogen has become dipole. So what would it do to the other hydrogen? What would it do? It would attract the electrons of this hydrogen. So this part has become positive charge. So now, so this is happening for very less amount of time, okay? So at any instant of time. So now there can be weak forces of attraction between the positive and negative charges of the two hydrogen. And this forces of attraction is called as instantaneous dipole-induced dipole interactions. Okay, and this is the weakest among all the other van der Waals forces. Okay, and it is also called by another name called London forces, also called dispersion forces. So students, this is instantaneous and takes place for at any instant. When the electrons are moving, sometimes it so happens that there is electron density at one side, so the other part becomes deficient of electrons, so develops a slight positive charge. So it becomes dipole for very small amount of time. That will induce the next hydrogen. So it will induce the other nonpolar molecule, and there is force of attraction between the two molecules, resulting in London forces or instantaneous dipole-induced dipole interactions. I hope all the 5 types of van der Waals forces is clear. Okay, so which is the strongest? We have gone in order only. Ion dipole interaction is the strongest. Next one is dipole-dipole interaction is strongest. Next one is ion-induced dipole interaction. Next one, dipole-induced dipole. And the weakest is the London forces. I hope you all understood, right? Let's practice some questions on the different types of van der Waals forces. Suppose you have a question like this. Compare the van der Waals forces in chloride ion and HBr. Now, chloride ion means it's an interaction between ion and polar molecule. Second one, bromide ion and bromide ion means it's an ion. Hydrogen molecule is non-polar. Oxygen is non-polar. Oxygen is non-polar. So, the interaction between ion and a polar molecule, we know that it is stronger than ion and a non-polar molecule. Yes, so if we look at the types, ion and first one is ion and dipole means it's polar. This is polar, this is polar. Right. The fourth one is polar and non-polar. The last one is non-polar and non-polar. This is ion and non-polar. Right. So if we check ion and polar is the first one. So it is the strongest. Next one is ion and non-polar. Next stronger. And the least stronger is non-polar. Right? That is the London forces. This is the London forces. This is ion-induced dipole. This is the first one. So if we know that 5 types of van der Waals forces, you will be able to compare. Okay. Second one is same question. You have to compare the van der Waals forces in HCl, HCl, polar and polar. Then I have chloride ion, CCl4. Then I have hydrogen and HBr. Okay, so over here, so let's take this is A, this is B, and this is C. Okay, so first one is between a polar and a polar. Second one is between an ion and CCl4. We learned in the dipole moment lesson that this is non-polar. Third one is between a non-polar and a polar molecule. So polar and polar, it is greater than ion and non-polar is the next one, and then non-polar and the polar is the third one. Okay, if you look at the different types, you will see that this is the order. Okay, so we already said that this is the strongest, this is the next one, this is the next one, this is the next one, and this is the least. Okay. Now, question number 3. So same question. Compare the van der Waals force in fluorine. Okay. Chlorine. Okay. Bromine. And iodine. Suppose there's a cylinder consisting of full fluorine. There's another cylinder consisting of full chlorine. There's another cylinder consisting of full bromine. And last one, full iodine. Okay. So how do you compare the van der Waals forces? Now, all are non-polar. All of them are non-polar. So the driving force is the same. Yes, that is London forces. Dipole-induced dipole. Non-polar and non-polar. It is London forces or dipole-induced dipole forces. Right. So how will we know? Suppose if the driving force is the same, we will check the molecular weight. So check the molecular weight. And van der Waals force is directly proportional to molecular weight. Okay, so this is very important. So this I will write it at the side. Van der Waals force is directly proportional to molecular weight. Okay, so now suppose I name this as, number it, A, B, C, and D. So iodine has higher molecular weight because fluorine, chlorine, bromine, iodine. As you're coming down, what's happening to the molecular weight? It's increasing. So A is less than B, which is less than C, is less than D. Why? We are checking the molecular weight. Why we are checking the molecular weight? Because the driving force is the same. All of them, they are non-polar. It is London forces. Dipole-induced dipole interaction. I hope it is clear. Right. So we'll move on. So I will just wrap this. So now we will look at some questions. Okay, so this I'm keeping this the same. Question number 4. So comparing the van der Waals forces for fluorine gas, chlorine, bromine, and iodine. Okay, now we saw that iodine has the highest molecular weight, so it has higher van der Waals force. And that is the reason why fluorine and chlorine, they exist as gas, bromine as liquid, it's a red liquid, and iodine as what? Solid. Why? Because of van der Waals force, which is higher for iodine. That is why it exists as solid, strong forces of attraction. Okay? So this was just an information. So this wasn't a question. I hope this is clear. Now, coming to Another condition, van der Waals force is directly proportional to boiling point. Suppose if any substance has, or if any between any two molecules, the van der Waals force is more, that means the boiling point will be more. Okay. So for example, if I have helium, neon, argon, krypton, xenon, and radon. As you're coming down, what is happening to the molecular weight? Molecular weight, as you're coming down, increases down the group. Right? So if it is increasing down the group, so what is happening to van der Waals force? Also increases down the group. So what happens to the boiling point? Boiling point increases. So who is having the highest boiling point? Radon is greater than xenon. I'm talking about the boiling point. Greater than krypton is greater than argon, is greater than neon, is greater than helium. So in simple words, van der Waals force is directly proportional to boiling point. This is the next condition. So all these conditions I'm writing out over here. So it's easy to summarize. So as you're coming down the group, what's happening to the molecular weight? Molecular weight is increasing. When it increases, van der Waals force also increases. So what happens to the boiling point also increases. I hope you understood. Okay. Then another condition that I want to discuss about is, we have not discussed much about the organic molecule, but this I'm rubbing, I've written it at the side. Okay. Now, for example, I take N-pentane. Pentane, maybe you will be knowing, made up of 5 carbon atom. Pent means 5 carbon atom. You will be learning more about it in grade 11. Okay, so I have normal pentane means it's a straight chain. So CH3 plus 1, 4. This is 2, 3, 4, 2, CH3. So 1, 2, 3, 4, 5 carbons. So normal pentane. This is first one. Second one, I take isopentane. One I'm drawing is isopentane. Okay. So in isopentane, it is branched. Okay. So there is branching over here. So okay. So if you look at the formula for normal pentane, it is C5H12. For isopentane also, the formula is the same, only the arrangement is different. So 3 to 5, 6, 7, 8, 9, 10, 11, 12. Okay. The formula is the same, only the structure is different. Okay. I have one more, which is called as neopentane, which is more branching. You will be studying about all these. Okay. CH3, C, CH3, CH3, and CH3. This also, the formula is C5H12. All of them, they are called as isomers, which have the same formula but different structure. Okay. So all are isomers. Now, if I ask you to compare the van der Waals force of normal pentane, isopentane, and neopentane. Okay. Now we cannot go with the molecular weight because they have the same formula, they will have the same molecular weight. Yes. And so they have, all the three have the same molecular weight. They have the same forces of attraction, that is the London forces. Okay. Instantaneous dipole. Okay. Now what you have to check. In this case, you can check the surface area. Surface area. What you would check? You will check the surface area. Okay, so these type of questions are very important. So I will write it here because I'm writing the conditions here. Van der Waals force is directly proportional to surface area. So that means here you can see normal pentane, it has more surface area. See, it is taking more space. So normal pentane will have more van der Waals force compared to which one? Among isopentane and neopentane. Isopentane is taking more surface. So next one will be what? Isopentane. Last one will be neopentane, which has the least. I hope it is clear. Okay. So boiling point, if normal pentane has higher van der Waals forces, the boiling point will be more for normal pentane compared to isopentane and neopentane. Okay. So whenever you see that the molecular weight is the same, the force is the same, you check the surface area. Usually for isomers, we check the surface area because for isomers, definitely the molecular weight will be the same. So definitely you will look out for surface area. So I hope this is clear. Similarly, if I take, for example, don't worry how to write the isomers, etc., because we didn't do the organic lesson still. We will be doing, and you will understand how to draw. Okay. So for now, I'm just drawing it for you. First, for now, just remember the conditions. Okay. Conditions are very important. Okay. For example, if I say butane means there will be 4 carbon. This is normal butane. This is straight chain. Normal butane. And I have isobutane also. That means 1, 2, 3, 4. Yeah. So this is the branched one. This is isobutane. Who will have higher surface area? Both of them are isomers, so they will have the same molecular weight. So who will have more surface area? Definitely normal butane. So the van der Waals force will be more. Okay. So for isomers, check surface area always. Because for isomers, molecular weight will be same. Because they have the same formula. I hope this is clear. And branching has lesser surface area. The normal one has the more surface area. Okay. Okay, students. Similarly, if I ask you to compare hydrogen chloride, hydrogen bromide, and hydrogen iodide, all of them, they are polar. Right? Hydrogen chloride, hydrogen chloride, hydrogen bromide, hydrogen bromide. Okay, hydrogen iodide, there are a lot of hydrogen iodide molecules. Okay, so they are all polar. So the type of force is the same. So they are all dipole or they are polar. So the type of force is the same. Next, check so the next one, what you would check is if the force is the same, you will check for the molecular weight. When you check the molecular weight, obviously, hydrogen is the same in all of them. Hydrogen iodide will have higher molecular weights. So it will have higher van der Waals force, then HBr, and then HCl. Right. But at the same time, this is correct. No problem in this. But if I have an additional hydrogen fluoride here, HBr, HI. In this case, also we follow the same order. All of them, they are polar molecule. So I have a lot of HF in a jar. I have HCl in a jar, HBr in a jar, and HI in a jar, hydrogen iodide in a jar. Okay. So all of them, they are dipoles. They are the same type of force is present, same type of force present. So we check the molecular weight. And obviously, in this case also, hydrogen iodide has the highest molecular weight. So the order is like this, right? But I want to tell you an exception here about hydrogen fluoride that forms hydrogen bond, okay, and which is considered to be strong compared to van der Waals force. Because it is forming strong hydrogen bond, there is a small discrepancy in our order. This order is wrong. Instead, we have an order like this. HCl is less than HBr, is less than HI, is less than HF. Or rather, HF has the highest van der Waals force, and then HI, then HBr, and then HCl. I hope I'm clear. Why this discrepancy for HCl? The order is the same like the previous one, okay, but for HF has the highest because of strong hydrogen bond, which we will be learning. That video is also coming soon. Hydrogen bond is a strong bond compared to, it is strong than, hydrogen bond is stronger than van der Waals forces. So the order of HI, HBr, and HCl is the same, only HF has higher van der Waals force because of the strong hydrogen bond exists between fluorine and hydrogen. Okay, sorry. The hydrogen bond I drew is wrong. So this is the reason for the discrepancy of hydrogen fluoride. Why? There is strong hydrogen bond in hydrogen fluoride molecule. So it has the highest valence van der Waals force. Okay, van der Waals force. Now I take one more example. So if I take, there's a question, if I ask you to compare the van der Waals force in hydrides of group 16. Okay, so I have water. Okay, I have selenium, I have tellurium. So here the forces is the same. So we check the molecular weight. When we check the molecular weight, this will have the highest molecular weight. So definitely the order of van der Waals force will be like this, right? But water also has strong hydrogen bond. So in this case also, we have a small discrepancy, and this hydrogen bond is stronger compared to what van der Waals force. So we have a small discrepancy. So our order is H2S. The other order is the same, no issues in there. So H2TE less than water. In group 16 hydrides, who has the highest van der Waals force? It is water. Because of what? Because of the strong hydrogen bonding. I hope it is clear, right? Now, similarly, so water and hydrogen fluoride, till now you learned these are the two compounds that show hydrogen bonding. Our video on hydrogen bonding is coming. You will be learning more molecules that have hydrogen bonding, okay? So for now, you remember these two examples. So that is why they will have a higher van der Waals forces. Okay, now coming to another question. Suppose I have to compare the van der Waals force in AlBr3 and AlI3. Okay, then I have magnesium chloride, magnesium bromide, and magnesium iodide. Okay, then I have beryllium chloride, then beryllium bromide, and beryllium iodide. Okay, I have lithium chloride, lithium bromide, and lithium iodide. Okay, suppose in the first case, we check the molecular weight because it's the same force basically. So we check the molecular weight and we see that aluminum bromide, it has lesser, iodine has a higher molecular weight. So aluminum bromide has lesser van der Waals force than aluminum iodide. Next one, here also the force is the same. So we check the molecular weight. Iodine has the highest molecular weight. So we put this in this order. Similarly, here also iodine has higher molecular weight. So we place this in the same order, right? Because we are checking what? We are checking the molecular weight, and molecular weight directly proportional to van der Waals force. Okay, in the last one also, lithium. Also we place it in the same order because iodine has highest molecular weight. Okay, but students, you must remember here, in all these examples that we have taken, there is a metal and there is a non-metal. We didn't talk about this metal and a non-metal. Okay, now here, so these compounds are formed between a metal and non-metal, and what you have to take care is for lithium, beryllium, magnesium, and aluminum, these are the halides, halides. Okay, so if you come across halides of these metals, lithium, beryllium, magnesium, and aluminum, okay, if we come across the halides, we take the van der Waals force is directly proportional to polarity. Polarity means difference in electronegativities. Difference in electronegativity. Okay, so what we have done is wrong. What we have done here is wrong, because whenever we come across the halides means for now we will consider the chlorides, bromides, and iodides of these metals, lithium, beryllium, magnesium, and aluminum. Okay, whenever we come across the halides of these metals, we consider what? We consider the polarity. So, if we talk about aluminum chloride and aluminum bromide and aluminum iodide, okay, the difference in polarity is more, or polarity is more for aluminum chloride because the electronegativity difference is more. Chlorine is highly electronegative compared to bromine and iodine. So that means this aluminum chloride is more polar. So aluminum chloride has more van der Waals force compared to the other two. Okay, I hope it is clear. So you have to basically, this is an exceptional condition where you need to check what? You need to check the halides means you check chloride, bromide, and iodides of lithium, bromine, magnesium, and aluminum, exclusively these metals. So in that case, what do you check? The polarity, the difference in electronegativity, which halide is more electronegative. Okay. For example, the second one, magnesium, I'm not talking about the fluorine now. I have an exception there also. Magnesium chloride, magnesium bromide, and magnesium iodide. This is also a halide of magnesium, okay? So, which is an included over here, see magnesium, right? So here chloride is more electronegative. So that means this will be the order. Okay, so please remember this condition. Otherwise, you will quickly answer that magnesium iodide is highly, you will say that magnesium iodide has higher van der Waals force. No. So beryllium, magnesium, aluminum, and lithium, halides. Please check the polarity. Halides means which all halides? Chloride, bromide, and iodide. So I'm repeatedly saying this. Okay, so this will be more polar, so hence higher van der Waals forces. Okay, similarly, if I talk about beryllium chloride, beryllium bromide, and beryllium iodide, also the same. Beryllium chloride has higher electronegativity difference, so higher polarity. So this will be the order. Similarly, lithium chloride, lithium bromide, and lithium iodide. Here also, lithium is also a metal that is included here. And chlorine is highly electronegative compared to the other two halogens. So this will be the order. Now, why this discrepancy or why this exceptional behavior? Because lithium, beryllium, magnesium, and aluminum halides. Halides means which all halides have I included? Chloride, bromide, and iodide. All these, although they are ionic compound, they have more covalent character. They are ionic, but what nature they display more of covalent character. We learned this in Fajan's rule, right? So these halides behave in a different way because they have more of covalent character, although they are ionic compound. And I told you one exception here also. An exception to this is fluoride. Okay, so if I take lithium fluoride, magnesium fluoride, aluminum fluoride, all these, they display more of ionic character. Okay, here also one more exception is there. So these are the exceptions that you have to memorize it. Okay, so lithium, beryllium, magnesium, and aluminum, the halides. Halides means chloride, bromide, and iodide. They show more of covalent character, and that is why you have to check their polarity for checking not the molecular mass. You have to check the polarity for determining the van der Waals force. Okay, an exception is fluoride. Fluoride is the fluorides of lithium, magnesium, and aluminum. They are ionic. Here also an exception. Beryllium fluoride is again covalent. So these few things you have to memorize. Okay, so these few things you have to memorize. So if you come across a metal and a non-metal, a metal and a non-metal, you check if it's a halide. If it's a halide of chloride, if it's a halide, that means whether it's chloride, bromide, or iodide of lithium, beryllium, magnesium, or aluminum. If that is the case, you will check for polarity, not for molecular weight. You will check for polarity for determining van der Waals force. Okay. And then fluorine is an exception. Okay. Fluorine, all the fluorides of lithium, magnesium, and aluminum, they are ionic. Okay. But here also exception, the fluoride of beryllium is covalent. This is an exception. I hope it is clear. You just have to memorize these few little things about this halides. Okay. So I will wrap from here and give you a few questions. So this I will keep it. So these informations I am keeping. Okay. Now compare the van der Waals force in first one. Chlorine molecule and bromine molecule. Both are non-polar. So the last type of van der Waals force, London forces. So we check the molecular weight. So when we check the molecular weight, who is having the molecular weight? So who has a higher molecular weight? Bromine. So definitely chlorine has a lesser, chlorine molecule has higher van der Waals force compared to bromine. Okay. The second one is oxide ion, water, interaction between ion and polar molecule, and ion and non-polar molecule. So this is an interaction between ion and polar molecule. This is an interaction between ion and non-polar molecule. So obviously, who has higher ion and polar molecule, right? So ion and polar molecule has, so if we have written the different types, ion and polar molecule, number 1. Ion and non-polar molecule is number 3. Ion and polar is number 1, right? So definitely who has higher dipole moment, ion and polar molecule, okay? Third one is aluminum chloride and aluminum bromide. We learned this type. The halides of aluminum, halides of aluminum, lithium, beryllium, and magnesium. We don't check the molecular weight, we check the polarity. So definitely we check the polarity, and chlorine is having a higher electronegativity. So aluminum chloride has a higher van der Waals force. Then the next one, helium atoms and argon. So we check the molecular weight. As you're coming down, the molecular weight increases. So argon has a higher molecular weight. So molecular weight is directly proportional to van der Waals force. So definitely helium has a lesser van der Waals force than argon. Fifth one, so I'll just wrap this part so that the conditions are visible for you. So I hope till here it is clear. So it's just a revision questions. So the fifth one, I have beryllium chloride and beryllium bromide. Here also, halides of Beryllium. Okay, we check the polarity. So definitely this one is more polar. So definitely beryllium chloride has a higher van der Waals force than beryllium bromide. So these are just some revision questions. Okay, sixth one, hydrogen and nitrogen. Hydrogen is non-polar. Nitrogen is also non-polar. So it's the London forces. So we check what? We check the molecular weight. So definitely hydrogen has a lesser molecular weight. So if the molecular weight is less, van der Waals force is lesser. Okay, now we have the next one is hydrogen chloride, hydrogen bromide, hydrogen fluoride. Okay, if the force is the same, okay, so we check the molecular weight. So according to the molecular weight, we check that hydrogen bromide has a higher van der Waals force than hydrogen chloride. Yes. But we learned about the discrepancy of hydrogen fluoride and also water, that they have hydrogen bonding. So comparatively, they have higher van der Waals force than the rest of the two. So hydrogen fluoride has a higher van der Waals force than HBr, which is having higher than HCl. For HBr and HCl, we follow the molecular weight. We check the molecular weight. Hydrogen fluoride, we check for hydrogen bonding. It has hydrogen bonding. And one more example we saw about water that also shows hydrogen bonding. That is why it has it is stronger bond. The van der Waals force is more there. Okay. So the hydrogen bonding is considered to be more stronger than van der Waals forces. Okay. Okay, students. So today we saw the van der Waals force. We saw the different type of van der Waals force. We studied some exceptions, and also we solved many questions. Okay, in the next video, we will be learning about hydrogen bond. Okay, so meanwhile, please keep studying and have a great day.